Have you ever wondered how our ventures into the cosmos might turn back the sun's relentless glare? Imagine scattering iron filings, tiny and numerous, across the expanse of low Earth orbit. Sounds like a page from a science fiction novel, doesn't it? Yet this concept isn't just a fantasy. It's a real proposition by scientists exploring geoengineering solutions to combat climate change. Iron filings in low Earth orbit, at an altitude of 250 miles, face a dance of complex orbital dynamics. These particles, rather than remaining static, would orbit Earth. For any geoengineering benefit, these filings would need to adopt a sun-synchronous orbit. Such an orbit keeps the filings consistently aligned with the sun, maximizing their shadow cast on Earth. However, achieving and maintaining this precise alignment is no small feat. The stability of these iron filings in orbit is another hurdle. Even at high altitudes, the thin traces of atmosphere create drag. This drag pulls on the filings, causing them to gradually spiral back toward Earth, a process known as orbital decay. To counteract this, one would need to continually replenish the filings, adding to the complexity and cost of the operation. Moreover, the logistics of distributing and maintaining a dense cloud of particles capable of reflecting sunlight effectively are daunting. The particles must not only be numerous but also maintain a configuration dense enough to cast a meaningful shadow. This requires advanced deployment technologies and substantial energy, pushing the boundaries of our current capabilities. Reflectivity and coverage are critical too. To reflect a significant amount of sunlight, the particles would need a vast collective surface area. Given the sun's apparent diameter of about 0.5 degrees, blocking even a portion of sunlight effectively would require an immense and densely packed cloud of particles. Introducing such a vast quantity of iron filings into space also raises significant concerns about space debris. These particles could endanger satellites, spacecraft, and even the International Space Station. The potential for collisions and the generation of additional debris present substantial risks. Furthermore, the environmental impact of deploying materials into space remains uncertain. As these particles re-enter Earth's atmosphere eventually, they could have unforeseen environmental consequences. This, coupled with the need for international cooperation and governance to manage the geopolitical and ethical implications, adds layers of complexity to the issue. While current research in solar geoengineering is more focused on stratospheric aerosol injection and space-based reflectors, the idea of using iron filings remains a topic of discussion. Each method, whether it involves sulfur dioxide in the stratosphere or reflective satellites at strategic points, aims to create a manageable and controllable impact on solar radiation. In conclusion, while the concept of using iron filings in low Earth orbit to mitigate solar radiation is intriguing and innovative, it is fraught with technical, logistical, and environmental challenges. The dream of maintaining a stable, effective reflective cloud in orbit is, at least for now, just beyond our reach. As we continue to push the boundaries of technology and science, who knows what the future holds in our quest to harness the power of our cosmos.